So this question's from Jeff. It's about graphing and transformations in VCE Methods. And he says that sketching a graph and mapping transformations is super tedious. Does anyone have any tips? So when sketching graphs or sketching equations that involve transformations, there's two key things that you need to know. The first one is, what is the shape of the original equation if it had no transformations on it? So for example, the base parabola is just the equation y is equal to x squared. So what are the features of that, and what does that look like in general? And then you have to be able to apply transformations on top of that. So the second thing that you need to know is how different transformations actually look on different equations. And all transformations are applied in the same way, but how they're reflected might be a bit different just depending on the algebra of your equation. But most of the time, the actual way that transformations are represented look very similar for different functions. So we'll go to a couple of examples once we get to the whiteboard. But we'll just look at what Finn commented. Using Kaz and other people said on my post can be quite useful at first, just to get an understanding of transformations before moving away from relying on the Kaz to just doing it on paper. So Finn's got a good point. Using the Kaz to actually understand how different transformations look on different equations is a really good way of understanding. But if you just have an understanding of the transformations and how you can essentially just imagine them, if you had transformations on a graph, you can imagine, let's say if you had x squared versus x minus 2 squared, which we're going to do on the Desmos graphing calculator. If you had something like that and you weren't familiar at all with how that would look, the graphing calculator is the best way of understanding what those differences look like. But once you understand like the basic premise of you have dilations, you have reflections, you have translations, and you know how they're reflected differently on different equations, then you don't really need the calculator too much. It's good to like double check you're working out more so than relying on your calculator to kind of know what the shape looks like. So we'll jump to the graphing calculator here. I've got x squared drawn right now, and you can see it's pretty expected. It's just a turning point at 0, 0, basic positive parabola. Now, if we add, let's just say a really basic transformation, which in this case is a translation, you can see that we have one change to the graph. And the only change to the graph is that it's shifted to the right by 2 units. So just based on these two equations that I've sketched and based on the resulting shape, we should be able to figure out what the minusing 2 does to our equation. And what the minus 2 does is it shifts the whole equation to the right by 2 units. Now, the reason why I've chosen this one in particular is because a lot of people do get confused with this one. And it's the fact that we're minusing 2, but we actually move to the right, which is the positive x direction. A bit hard to understand for most people, just because it's kind of counterintuitive. We're minusing numbers, but we're moving to the positive direction. It's just how the numbers work in this case. And we go through it with the transformation videos. We explain why it's minus for the x value, but if you have a value on the outside and you add it, then that's actually going to translate the graph upwards. So it's different for x than it is for y. And these things you can actually figure out by graphing, because if you can graph these things, then you should be able to get a graphical representation of what's going on. So in this case, we have minus 2, which shifts the graph to the right by 2 units. And then we have the plus 1, which shifts the graph upwards by 1 unit. So if you added one transformation at a time, then you'll be able to see what each of those things does. So for example, let's add a 2 and we'll see what that does. You can see that the turning point or the starting point of our equation didn't actually change. So this negative 2, 1 or this 2, 1 is going to be our turning point. And we should know this from turning point form as well. But what we saw the 2 do was it shrunk our graph or made it kind of narrower. And if we made the value less than 1, let's say if we made it 0.5, then you can see our parabola gets wider. And then let's just do one more transformation. Let's do a negative, and you can see our graph is just reflected. The turning point is the same. The width of our equation is the same, so the actual shape is the same. The only thing that's different is that it's reflected, so it's in the negative direction from our turning point. So if we can kind of practice applying all these to different equations, then we can see how graphically they look different. But these transformations that are happening, they're actually very standard, and it doesn't actually change a lot for different equations. So I'm going to change this back to 2 just because it's going to be a bit easier to use. So if we have 2 on the outside here, that's the same for all equations. In this case, it's x squared. But let's say if we had the square root of x, what a 2 on the outside does to a square root of x graph is exactly the same. It stretches the graph. A negative 2 does the same thing. It shifts the graph to the right by 2 units. And the plus 1 on the outside does exactly the same thing. It shifts the graph upward by 2 as well. So that's how we get to our kind of generic transformations, which is represented in this table here. This table was awesome. It's from the Cambridge textbook. I'm not sure if it's still in the new version of the textbook. It was in the old version of the textbook. So I'm just going to have some coffee. It's in the old version of the textbook, but pretty much I'll just explain how the table works. The first column is pretty self-explanatory. It just summarizes what the different transformations are. So you have reflection in the first 2 rows, you have dilation in the next 2 rows, then you have a reflection in the line y is equal to x, which is kind of rare to come across. I've maybe come across it once or twice when going through really old practice exams. Maybe it used to be in an old curriculum, but reflection in the line y is equal to x is pretty much just finding the inverse of an equation. And then you have the translations as the last one. So I'm not really going to explain what each of these does. Hopefully the graphical representation of what I just did before gives you enough of an idea. If you need more help, then you could head to the transformation sections of our free VCE Methods school, and you can head there to see a whiteboard explanation of what's actually going on. So yeah, this table summarizes pretty much everything you need to know. The first column is the mapping. So that's what's actually going on in terms of the transformation that's being applied. Then we have the rule. So as we should know, x dashed is kind of the transformed version of x. Y dashed is the transformed version of y. So these have algebraic representations that go along with them. Again, I'm not going to show you in this video how they're actually applied. Feel free to head to the transformations whiteboard video to see that. We also have the matrix notation for transformations. This, I don't think it's in the course anymore, applying transformations via matrices, but it's just a cool thing to know that you can kind of do transformations a lot easier and kind of combine them all to one equation if you do use matrices. But yeah, we don't need to know it, I'm pretty sure, for the new 2023 curriculum onwards. So that would be this year's curriculum or whatever year you're watching this. I think that should be relevant to you. The most important one that I want to bring to your attention is the last column, because the last column is a really quick way of not only applying transformations to an equation or a function, but if you can work backwards, then you should be able to see what each of these features look like on different equations. So let's start off with the really easy one, which is the first one. So what we have here is a reflection in the x-axis, okay? So I'm just going to sketch a Cartesian plane really quickly. So Cartesian, no, that is really wonky. Let's try and redo this. Yep, cool. Okay, not bad. So let's just start off with our really basic equation, y is equal to x squared. So that's going to look something like this, right? So y is equal to x squared. Now, if we have a reflection in the x-axis, we should kind of know from intuition that the graph is just going to be reflected in the x-axis. So the x-axis is going to be our mirror. So the x-axis is this here. And then our reflected graph is going to be going downwards like that. Okay, so this is going to be our reflected equation. But how do we actually get our equation if we needed it? So what we can do is we can apply these rules here and then do some long algebra. Again, I'm not going to go through the process of that, but what the last column does very conveniently is it tells us exactly the algebraic operation to apply to actually get your image equation or your equation after transformation. So you can see here that what it says is that y is just going to be equal to the negative of the whole equation f of x. So in this case, when we started, f of x was equal to x squared. So if we want to get the equation of the image after the reflection in the x-axis, all we have to do is just make our whole equation negative. So what we say is that the image equation, we'll maybe call it something else, g of x is going to be equal to negative of our whole f of x, which is just x squared. So this is our image equation. And you can see here that this is done very quickly, and you don't have to go through any hectic algebra. And you can kind of memorize this table as well, especially if it's a tech-free exam. You don't have to go through the whole process of applying a whole set of transformations through the rules. Again, it's a very tedious process. You can just apply it through these kind of convenient ways of representing transformations, which are kind of simplified for us. So let's go through another example, and then we might do two at the same time, just to show you how it actually works when you have multiple operations happening at the same time. And I might go away from x squared because most people would be familiar with that. Maybe I'll go through, I'll use a square root graph or something along those lines. So let's do a dilation by factor Actually, let's do this one because this is one that a lot of people get confused with, and you'll see why. Dilation by a factor of a from the y-axis. Now, kind of unintuitively again, when you have a dilation by a factor of a, you're actually multiplying the x value. And the reason for that is because if you multiply the x value, then you're stretching it outwards like that because the x is in this direction. So if we multiply the x value by 2, then it just stretches the value 2 times to the right. And if you imagine what direction that arrow is, it's in the x direction, but it's actually coming from the y-axis because you can imagine the y-axis is here. You're multiplying to stretch away from the y-axis, which is in the x direction. So sometimes you might see dilations said, they might represent dilations as from the y-axis or in the x direction. They're actually both the same. From the y-axis or in the x direction, they're both the same. Okay, don't confuse from the y-axis as in the y direction. They're not the same thing. So from the y-axis is the same as in the x direction. From the x-axis is the same as in the y direction. Just to clarify that for a lot of people who might be confused with that. And personally, I was confused with that when I was doing VCE methods as well. Okay, so dilation by a factor of a from the y-axis, unintuitively, it multiplies the x value, and you can see it represented algebraically like that. So what we can imagine is that if we have our square root graph, so our original equation is f of x is equal to square root of x, and then we have a dilation by a factor of 2 from the y-axis, so I'm just going to say d by a factor of 2 from the y-axis, then the image is going to be g of x is equal to the square root of x on a. Because what I've done is I'm saying that g of x is equal to f of x on a, which is pretty much saying that you just replace x with x over our dilation factor, which in this case is 2. So I've actually just written a as my generic parameter, but I should have said the square root of x on 2 as my final image equation. Again, you don't have to go through any hectic algebra to do this. You can just read off the table and write it straight away, which again, I think is very convenient for us to do. So let's just do another quick example where we have a combination of multiple transformations. And what we're going to do is do this order first, and then we're going to switch the order and see that how that's actually represented differently when we get our final equation of transformation. So what we're going to do is start off with f of x is equal to the square root of x, and then we're going to apply our dilation by a factor of 2 from the y-axis. So if we look at our table, dilation by a factor of a from the y-axis, how the equation changes is that we have f of x on a. So whenever we have x, we just replace it with x over our dilation factor. Our dilation factor in this case is 2. So therefore, what this is going to become is the image, I'm just going to label it as g of x, is equal to f of x on 2, which is just going to be the square root of x on 2 like that. Now, if we apply our translation on top of that, then what that looks like, if we look at our table, is f of x minus h. So when we move to the right, we minus that h value, or we minus that translation value. So this one is going to be h of x is equal to g of x minus 3, which becomes the square root of x minus 3 divided by 2. Yep, that sounds about right. I really don't need the brackets on the numerator, but you get the gist. So this is our final equation after applying all of our transformations. So we had the dilation first, and we had the translation second. Awesome. Now, the reason why I labeled these all different functions is just to make it clearer. You don't have to do this, but it's just to kind of show you an illustration of what's actually going on. But hypothetically, if I were doing this question, what I would say is I'll just go straight to my final equation, and I would say y is equal to f of x minus 3 on 2, just like that. But the thing is, the reason why I split it up is because a lot of times people do get confused with the translation. Does it go on the x or does it go on the outside? If you split it up into multiple steps, that solves that issue. Because as you can see, what I did was I labeled this one g of x, and then that kind of simplified my notation when I made h of x. It's just g of x minus 3. And it's very clear if I split it up like that, that x minus 3 goes on the numerator. It actually doesn't go on the outside. Cool. Now, as I said, let's do the opposite order. So we're going to do exactly the same transformations, but we're going to do it in a different order. So we're going to do t translation of 3 units in the right direction, and then we're going to apply our dilation by a factor of 2 from the y-axis. So again, we're going to do the same thing. Let's go to our table, f of x minus h. So that means that our first image equation of our first step is going to be g of x is equal to f of x minus 3, which is equal to the square root of x minus 3. Awesome. And that makes sense. Translation -3 from the x value, we're shifting to the right. Now, if we apply our dilation on top of that, what happens is that we get h of x is equal to g of x on 2. And then that's going to become x being replaced by x on 2. So now we actually don't have our full fraction. We just replace the x with x on 2 because we only apply it to the x value. We don't apply it to everything under our square root. So this actually becomes x on 2 -3. So it looks slightly different. And that's because we applied things in different order. And because when we did our translation, and then when we do our dilation on top of that, that actually influences what the translation value is. Because you can imagine if you translate something and then you stretch it out, then that translation is going to be affected. But if you do the dilation and then the translation, then the translation is not affected by the dilation because the translation came last, if that makes sense. So that's why it's important to note the order of transformations. So in this case, our final image equation, if we want to represent it in functional form, is y is equal to f of x on 2 -3. I believe so. Yeah, which looks slightly different to this, but that slight difference does make a huge difference when it comes to getting your final equation.